I'm really lucky when she helps me with the magic, which doesn't, it happens whenever it's convenient to her, which is almost never. She's my familiar. She's a cat. So give it up for the cat, who does not want to help unless it's convenient to her, and who will be doing the presentation if I can't. But it's telepathically, so you'll have to also be a witch to understand it. So if you don't hear anything, that's on you. I'm sorry, I can't translate. Also, any Linux audio people in the crowd, great excuse to use there too. But we're getting there. Cool. Well, we will be talking about the Linux on the M1 effort. I can say ahead of time that we've achieved a lot since last year. We went from basically nothing working, and you were all impressed by GNOME running last year, to we are now a conformant driver. Like officially conformant, like Kronos recognizes us, like we can use the OpenGL ES trademark, which I totally should. Anyway, GLES 3.1, currently working on 3.2, and we're going to talk a lot about that today. It's not in the slides, but Carol should be out there in the audience somewhere, probably. Hi, Carol, yes. Carol went off and did OpenCL on Asahi, and I don't know, apparently most of the CTS passes and GPT-2 runs, is that right? I'll take it. They're 2,000 tests. That's pretty good. That's like an A+, yes. Yeah. Somehow managed to pass CTS without a spiller. Don't think about it too hard. Glass CTS is an interesting bunch. Vulkan will not be so kind to us. And we will talk about Vulkan will not be the subject of this talk. Very sorry. So yeah, we still going? Okay. At any rate, as it seems I will still be stalling, and I ran out of kitty-related material. I don't know. Not really sure what's happening here. Magic is a very fickle thing. I would just wave. Sometimes I wish I could just wave my magic wand to make the tech difficulty go away, but no. If the cat did it, it might work. She's better at this than I am. But anyway. I should clarify some additions to the outfit. The wand is real magic, the cat's real magic, the hat's just decorative. In case anyone's been wondering. But that was a good sign.
Can you hear this? Can you hear this? Can you hear me? Can you hear some feedback from you? Are we trying to use this? No, we can use that. I'll just use my. Okay. Hello. Is that Rose? Can you hear this? Can you hear this? Let's try the other device. Can you hear this one?
And I guess we might as well talk about Vulkan while we're waiting as well, because there's not much in the slides. But this is the number one question we get asked: when will it run Vulkan? Second only to when will it run Steam. But those are kind of the same question, honestly. Somebody asked me today that I seem to think that DXVK is the most important graphics application in the universe, which, fair enough, I do seem to think that. And they asked me, name a single DirectX game. And I don't play games, I don't know. But Vulkan, I don't know. Carol did CL. I've been hacking on GL and the compiler and reverse engineering and all the other stuff. What's up with Vulkan? Well, we've got Ella somewhere out in the audience.
Oh, now it works. Now it works.
Am I hearing things? Sometimes you just hear it, Ella's somewhere out here probably, who has spearheaded the Vulkan effort. And we've got a bunch of other people who've been helping out with that, some of whom are here, so hello. We've got Rose. Have you done
I'm
Vulkan
hearing a
stuff?
lot of talking.
No Vulkan U. Mary's done some Vulkan stuff. I don't know. That's your turn. I did the reverse engineering and the compiler and the GL reference code. Now you get to write a Vulkan driver. It should be fun. Hey. And I don't know if I'm just supposed to run through my prepared material, but trying not to waste too much talk time while having hallucinations of Lina speaking into the ether, which I'm actually quite used to. We have a lot of phone calls, but it's a little different this time. Yeah. Any questions? Thanks for coming to the talk. I am happy to answer questions. I feel weird just standing here. Yes.
There's an IT assistant in the room.
Sorry?
There's a computer engineer or IT assistant in order to help in the room.
I'm sorry, I can't understand it.
It's a joke that there's no computer engineer in order to help.
Oh, yeah. Alas. Yes.
Commented that the hat's just decorative. What about the cloak?
We don't talk about the cloak.
Right here on the screen.
We've got video.
No video? Yes?
Yes, video.
This video? Okay.
And I will let Lina take it away.
Good on that. Alright, we have, okay, I am hearing myself, but that's probably not much I can do about that.
Sorry?
Alright, are we good?
I think so. Yeah, take it away. Lina. Woo.
Yeah. We're live, right?
Can she not hear us? I'm confused. Should she? Lina, can you hear us?
Yes.
Okay, hi, yes. Take it away.
Alright, let's go. Alright, hello everyone. It's Lina here. I was here last year, talking about our little, Rust driver for the Apple GPU, and, we're gonna give you a little update on how things are going. So, yeah, last year when I did a talk, this is about where we were. So we had a desktop, we just had gotten things running. And at the time, that driver had, lovely things like blocking submit, so no sync, who needs sync when you can just block for the GPU anytime you give it work? And we were shutting down the GPU every single submission because there was a bug with TLB invalidation, which is really funny. And even then it was running at like, over 30 FPS. That was only on the M1 originally. We didn't have support for the other GPUs or anything like that. So now, fast forward another year, and we are now conformant on all Apple Silicon GPUs, all the Mac ones anyway, across 2 firmware versions, because we have to support multiple APIs. We have explicit sync with firmware scheduling. We're actually faster than macOS for some workloads, I think, was it Xenotic was running faster on Linux than macOS. The UAPI is Vulkan ready, and we actually have a work in progress Vulkan driver. And the kernel side is 18,000 lines of Rust plus the abstractions. So one of the cool things is that it's super stable. People always talk about, like memory safety and Rust and all that, and how that can benefit, kernel development. And so we really, noticed that when we started, because we got from the, first cube rendering on Linux to a stable desktop in just a couple of days. And I think that's pretty unheard of for, kernel GPU driver development. So we've been shipping this to Asahi users since December. I've actually been streaming from an M2 since then, and I leave my streaming machine on for months at a time, and it's fine. And as far as I know, we've had 0 kernel oopses reported in the wild from users, excluding 1 DRM shed issue with Firefox, and and not counting GPU firmware crashes, which are also rare. But like the actual driver, the logic and the memory management and all that, we've had zero, like problems there. So last time I talked about the versioning magic that we have for the Rust driver. So we have basically conditional compilation, like on a line, on a statement, or even sub-statement basis for different firmwares, because that way we can support multiple API revisions and different firmware versions in the same driver. Without having to like copy and paste huge structures and things like that, or doing like build system level conditional compilation. So we have all the differences written into the same driver, and we support 3 major firmware API branches, I guess you can call them, across 2 different firmware versions. So G13 is M1, 14G is M2, and 14X is M2 Pro Max. And basically what ends up happening is that we compile every API-dependent part of the driver multiple times, and it works. So we even have some major changes between versions. So on everything before M2 Pro Max, most of the render configuration was in a big structure like that. So it's a lot of fields and a fixed layout structure. For G14X for M2 Pro Max, they switched to a register write list. And that's, it's still, these 2 screens are literally just adjacent in the driver. And there's the conditional combination at the top, and it works. And, we can do major changes in structure layouts. And yeah, it's fine, it scales. So a few updates on Rust for Linux. So one thing is that we got rid of place. So say hi to Pin in it. We have, basically we replaced, I used to have a big macro, I don't remember that. That was, how was that? Basically, we had a big macro that was used to initialize CPU structures on the heap. And that was a bit messy and kind of a hack from my driver. So now we have an upstream implementation of that called Pininit. And so that can initialize complex types on the heap, and it composes properly. There's no more unsafe or anything like that. And it's already upstream. So before that, we used to have something like that, where you had to use unsafe to initialize like a convar and a mutex, and it was a pain, and it wasn't nice. And now it's just that. Now you can just use Pininit, and there's an interesting syntax there because it's a macro, and it will initialize your mutex on your convar, and it all works. So another trick that we have for Rust is that we have extra lockup checking. So this is an interesting little thing. So how does that work? What we do is that we can set it up so that, for example, every time you create an arc, on the first execution of that line, it will create a new lock class for that arc, for that instance of the, not instance of that call site on the arc. And there's no macros, there's no API changes, there's nothing else. And the magic part is that on every arc drop, lockup engages, so it will do a fake lock, and that way we can discover locking violations that are triggered by, dropping references. So even if you have a drop code path where you're dropping a reference, but it's usually not the last reference to be dropped, you can still check that if that were to be the last reference to be dropped, that you would not be having any locking violations due to running the cleanup code. So that's pretty cool. So the funny thing is how this is implemented is using a Rust feature called track caller, which basically gives you the file, line, and column information of a caller to a given function, and it can propagate across functions. So you don't need any weird magic along the way, any macros or anything like that. The only annoying thing is that, well, it is file, line, column, so we need to map that to a lock class. So there's an ugly open-coded hash table to do that. But, it's locked up. Like, it doesn't have to be perfect or, you wouldn't run it in production. It just has to work and find the locking bugs, and that it does. So the fun thing is that when I enabled this in my driver, I actually found 0. zero bugs related to that. So I think that's another thing that would not have been talked about Rust, but I think the Rust coding style does actually encourage locking hygiene, so that's pretty cool. But don't worry, it is going to be a mess when we add the fence signaling rules, because right now we are not following, the whole don't allocate on fence signaling paths. We have a few issues there. All that will be cleaned up in due time, and I guarantee there's bugs there and locking issues. So don't worry, it's not perfect, but it works. So on challenges that we have, we need more reviewers because there's a lot of code to review. There's a lot of abstractions. There's a lot of dependencies to upstream, and it is kind of a chicken and egg problem. Because, we have a lot of dependencies and people want to see the user of the dependencies upstream at the same time. But if it's a giant patch series, that's really hard to review. So, help here is always appreciated and really helpful. The other thing is that chasing unstable Rust features is a little bit painful. So, for example, the latest Rust update broke our device ID table generation because that relied on const traits, which are getting apparently rewritten in upstream Rust. And so for the time being, it's kind of broken, and I'm going to have to figure something out there. So part of it is, just figuring out how to have that, like reduce the number of, unstable features that we use. So coming up, new things for the driver, we're going to be rewriting the page stable management in Rust because that is using IOMMU common code right now, but it turns out that we need too many fancy permissions and too many weird combinations for it to make sense to keep using that. So we're just going to rewrite it inside the driver. And also, I'm going to be integrating the GPU VA manager. I think it's not upstream yet, but it's being reviewed. So that manages all the page tables and address space for mapping BOs, partially and fully and all that. And we need that for Vulkan VM bind support. So that should be really good because the MMU code is like the first part of the driver that I wrote. So it's like the youngest. The MMU, the BO mapping, tracking and all that. So VM bind and GPU VM manager are going to clean that up a lot. And more upstreaming cycles. So I think it's time to hand off to Alyssa for our side of this whole little adventure.
Oh, wow, we got 4 hats going at once. All right. Pretty good. All right, let's get this started. Just magic. I don't actually even need the wand. It just comes through the veins, but it looks better with it, Anyway. So we already talked about the status, but yeah, last year we were kind of working at less, I don't know, and this year we're conformance. That's pretty cool, and we're shipping OpenGL 3.1. But actually, we have a branch working with 3.2, and what's the big difference? Well, it's everybody's favorite shader stage that everybody loves to use for absolutely everything. Not that slide. Let's go forward. Geometry shaders. We all love geometry shaders. Everybody thinks we should just use geometry shaders for absolutely everything. Like if you have a triangle, you know how you should draw that? With a geometry shader. You know why? Because it has geometry. At least that's what game developers seem to think, because they're everywhere. And they're required by GL 3.2, by DX10, I want to say, and by extension, if you want to play DXVK games, VKD3D games, whatever, you need your geometry shaders. And let's talk about geometry shaders. So yeah, real things use them, unfortunately. Like Blender. Blender loves geometry shaders. We have a tepid relationship with Blender. The good news, so I will say off the bat, the Apple M1 does not support geometry shaders in hardware, and it does not support anything even remotely like geometry shaders. I mean, if you look at like an AMD GPU these days, the important part isn't that they literally have a geometry shader stage, it's that they have, the NGG, next generation geometry pipeline, upon which you can efficiently implement geometry shaders. And no, we don't have any of that. We're funny off in Apple land. But the good news is that they are slow everywhere, so they just have to work and it'll be good enough. And we have so much memory bandwidth to waste on the M1 that we should be fine. So, what about mesh shaders? And I'm sure many of you are thinking, well, great, we'll just do geometry on mesh shaders. Bad news, we don't have mesh shaders either in the M1. Womp womp. Apple does advertise mesh on M1, and it's all software. And doing software geometry shaders layered on top of software mesh shaders, layered on top of compute on vertex, sounds like a way to make your FPS go not stonks. So let's not do that. The Apple M3 will have mesh shaders. I know the M3 hasn't been announced, but don't worry about it. There's telekinesis, telepathic magic, you know? No, the new iPhone has mesh shaders and hardware, so the M3 will too. But the other part is that mesh shaders do not help us with transform feedback. The hard part in all of this is that geometry shaders can emit a dynamic number of vertices and a dynamic number of primitives. They have to declare the maximum amount of data they emit, but they do not have to declare how much exactly they will emit. They can emit fewer than that. So they might say they have a max vertices of 16, maximum 16 output vertices, but they might only emit 3 vertices. So if we layer on top of mesh shaders can do the same thing, so that's fine for emitting geometry. But the problem is transform feedback, because transform feedback is specified, for those who are uninitiated with another one of our favorite OpenGL features, transform feedback, otherwise known as stream out in Direct 3D. So to stream out, the way it works is, the way it's supposed to work anyway, is that the first invocation of the geometry shader writes out all of its outputs to the buffer. And then the next invocation writes everything immediately after that, and so on. So everything is nicely in sequence. The problem is that GPUs are massively parallel. So if you want to implement that, you have to finish the first geometry shader invocation before you can start the second one, which is a complete serial bottleneck, and then your FPS goes not stonks. And the desktop vendors have significant amounts of hardware to sort out this whole mess. AMD, for example, has a very magical ordered append instruction, which is how they implement transform feedback. But the bottom line is that we need to know how many primitives the geometry shader will have written before it runs. So kind of a fun problem there. And layering on top of mesh shaders does not help us. There is a certain competing implementation of a Chronos API on top of Apple hardware that has now opened pull requests for geometry shaders and transform feedback and does not seem to handle the interaction. And they're doing it on top of mesh shaders, but on top of the double emulation, that does not help them with the hard problem of transform feedback. So not really a solution that we care about because we're a conformant driver and we're playing with the big kids. So what's the idea? Well, the idea is that we can run the vertex and geometry shaders as compute shaders or as vertex shaders if you want, doesn't really matter. So the geometry shader, we compile into a compute shader that will run once per input primitive as it's supposed to. It will write out its outputs into some buffer we allocate. It will generate an index buffer, so we can specify that whatever the primitive topology is and whatever the primitive we want is. And finally, it will generate an indirect draw. So all of the vertices and geometry we generate on the compute shader, we feed back into the 3D pipeline with an indirect draw. So far, so good. And then we just draw with a very simple vertex shader, which just reads from our geometry buffer and copies it directly into the 3D hardware. Fine. Pretty terrible. FPS go not stonks, but it'll work, maybe, sort of. The problem here is, again, we don't know where to write. And particularly when we have transform feedback, we need to write immediately after everything previously. So we need to know, so invocation n needs to know how many primitives were written by everything from 1 through n-1. So what are our options here? Option 1 is we cry and run everything in a single threaded shader and FPS goes not stonks. Option 2 is we are wrong and we fail conformance, something that, there's a particular emulator that just did a macOS port and that's their solution. It's just broken, but it's fine. Don't worry about it. They don't have to pass CTS. It's fine. We have to pass CTS. So what do? We could strip down the geometry shader to just figure out how many vertices it writes or how many primitives it writes, and we could run that in a loop. at the beginning, but then we still have n squared invocations over the whole, on squared invocations over the whole program, and that's not good. So no matter what we do, we can't do this in one pass and get it right and get it efficient. So what's the solution? We are going to introduce a geometry count shader. So the count shader is a geometry shader that does not write any varyings, any vertex outputs, anything. All it writes is the number of vertices and the number of primitives that it would have outputted if you ran the real geometry shader. So this is pretty easy to do in the driver. We take the geometry shader and we delete everything but the stores. We delete all of the stores and we just keep the set vertex and primitive count at the very end. And then we let dead code elimination go to town, and usually it deletes the whole shader. Or there's a little bit of control flow. We get something very small, and this is the count shader. So we run this, and then we sum them all up into this count buffer, and so now we can read in constant time for any invocation how many vertices and primitives came before it. So it's a multi-pass approach now. We have basically 3 compute dispatches we need instead of just 1, but here's the good news. The count shader, every geometry count shader is running in parallel for all the primitives, so we get good use of the hardware. The geometry shader itself, everything is running in parallel. We get good use of the hardware. So these are both working the way they want them to. So the only question is, how do we do it? How do we do this count? Because it seems like adding up all the things before it, that's inherently serial. Great news, it's not. This is known as a prefix sum, and it is one of the most classic problems in parallel programming. How do you do a prefix sum on a parallel processor? It turns out there are efficient implementations. There's a really great single pass one. It is broken on the M1 because of hardware issues, but it doesn't really matter. At minimum, you can use subgroup ops to accelerate things. So in theory, at least in theory, we have a fully parallel thing, another fully parallel thing, and one more fully parallel thing, and so we got rid of our serial bottleneck. And then we can just implement transform feedback correctly, and yeah. So, and just for the record, this code works. It passes CTS. It will ship probably in the next few months or weeks or something. And yeah, let's talk about keeping this clean, because this is a mess. We do not want to write this all in NurBuilder. This is thousands of lines of code, and you do not want this in NurBuilder, which is effectively writing assembly with C macros. Everybody's favorite thing to do. Definitely the right way to program. No, let's just write C. We can just write C, and but compile the C for the GPU, like we're writing a shader. And then we can have a little bit of magic code, which is our specialty here at Asahi. And our magic code will automatically generate bindings for our C code running on the GPU to NurBuilder. And this is a fully generic piece of code, which I am hoping I can nerd snipe every other driver into using, because it is phenomenal and is a massive time saver. And yeah, so let's look at what this looks like. I think it's the next slide. So this is a bit of C code. This is libagx end primitive. So this is the guts of the implementation of the end primitive function in a geometry shader. And so it takes in a bunch of parameters that we calculate in the compiler side, and it does a little bit of math, and it writes out the index buffer, because the end primitive is supposed to fill out a bunch of indices for generating a triangle strip, and then it ends the strip, and that's just an index buffer with primitive restart. So we just write out the primitive, and we do the primitive restart. Detail's not important. What's important is that this is a single screen full of code, and just doing a single for loop in NurBuilder is about a screen full of code. So big improvement there. And on the compiler side, it is completely seamless. Our libagx end primitive function is now a libagx end primitive function, but now it's on the CPU instead, and we call it from the compiler. We did not write a single line of bindings here. It was all automatically generated by spurvy to Nur at build time. So a pretty big improvement. And yeah, so that's the idea, but talk is cheap. Show me the results. Hey, Lina, open Blender, if you can. I think you can hear me.
Fast. All right, let's just give Blender a shot. Let's see if that works.
And this is and Blender makes heavy use of geometry shaders, working full speed on the M1.
Yes. So we can do that. We can use this if that is geometry shaders.
And
It works.
thank you. Also,
Yeah, what was it?
also, I'm sorry. No, mostly I'm sorry.
Which one
Yeah,
did I
mostly that
ask?
one. Yeah. Anyway, so that's geometry shaders, and I hope I haven't scarred you too much because next year we will be talking about tessellation shaders. Just kidding. Well, maybe. Probably not. There's a reason I just built a C compiler for the whole stack. Anyway, thumbs up. Any questions now that you've seen the inside of this nonsense? Yes, Friedrich.
So when you see this, when will there be ray tracing?
Hey, you want to work for our team?
I mean, I guess I won't do the entire ray tracing thing, but if you need help with one specific thing, you can always ask.
That's how it always starts, yeah. I just wanted to give Marcan help with one little thing with the getting some pointers on getting started with Mesa, and now I've just implemented geometry shaders in software, so be careful with one little thing. My advice.
Thank you.
What happens if the number of primitives emitted is the result of an atomic operation in the geometry shader that might be different on the second execution?
We cry. So currently we're not exposing vertex pipeline stores and atomics because it's optional in GLES, and I didn't want to think about that because it makes my head hurt. The longer answer is that at least the Vulkan spec is very unclear on what happens in this scenario, because it says that you can execute geometry shaders multiple times, or at least it's implied that you can. And if so, my interpretation is that putting 2 and 2 together, if you do that, you're invoking, the app has done an undefined behavior, and it's not my problem anymore. I may be wrong.
I'm not sure that's actually quite correct, because I think each individual invocation still has to work, and by splitting it in 2, and you're kind of breaking that. But yeah, I don't think apps are actually going to hit that very likely. But I guess
my interpretation of the spec, which I chose after I came up with this plan, as one always does, is the spec says that the implementation can invoke these shaders multiple times, and if the app is because of that, all bets are off if you have different behavior in each time it's invoked. And the whole reason why we have that clause in the spec is so apps don't expect their atomic add to do the right thing in a geometry shader. And I don't know. I will be very sad if the alternative is to just start serializing things or start copying things like crazy. And unless there's a CTS case that tests this and an app or an app that tests this, I will choose my version of the spec. Thanks very much. Yeah.
So obviously transform feedback has a lot of deserialization concerns, but also like normal draws, you have very similar things because like draws in order have to override. And I was wondering, do you use the same mechanism there? And if you do, like, how do you figure out how large your buffers have to be, like, where you store your geometry shader outputs?
Oh boy. Well, first of all, in terms of where we actually write in the buffer, the index buffer we're doing is fully packed. The generate index buffer is fully packed using the exact same prefix sum infrastructure. This could be optimized, but I had to type all that code for transform feedback. Might as well use it for this. But for allocations, right now, we hope for the best. As soon as you start using geometry or tessellation, we allocate a big buffer, and we just have a watermark? No. The name is slipping me. I did not get enough sleep last night, but we just allocate directly from the buffer on the GPU. And if you run out of memory, sucks for you. I'll deal with that when we get there. There are ways to do much better in terms of the memory usage. At some point, this is sort of unavoidable. The real problem here, what I really want is dynamic memory allocation from the GPU. If this were Mali, Panfrost would support that, and we can do that. As it turns out, doing dynamic memory allocation from the GPU completely violates all of the DMA fence locking rules, which Lina will not want to talk about, I'm sure, because we're all scarred from this. Lina, Faith, Saima, and I had a meeting a few months ago where we tried to figure out how to do geometry shaders with dynamic memory allocation. And no, the answer is, as soon as you start doing dynamic memory allocation, you're going to get deadlocks. Also, Panfrost is definitely broken in the kernel, sorry. So no, we're eating it now, as the kids would say. I'm the kids.
Apple does do that. I don't know how they handle their locking and their rules, but they actually do allocate in the kernel from a callback from the GPU. And we were thinking we could try to implement that, but yeah.
I see no hands, which means you're all sufficiently scared of what has just transpired. She's a witch, burn her. I earned my black magic designation. All right, well, that's the wrap. Thank you.
Hey, everyone!
Yeah.